Last time we talked about recursive algorithms, and this time we're going to talk about how to prove that a recursive algorithm actually does what it says it does, what it claims to do. And we call this a proof of correctness proof, and we will be using induction to perform these proofs. So remember this algorithm that we talked about last time. It was an algorithm to reverse a string. And so what we would do, and I'll go over it here in a minute, but what we will do in the next slide is prove that this really does what it says it's supposed to do, and it's supposed to reverse a string. So that would be what we'd be trying to prove. We'd be trying to prove, does it really reverse a string? So let's remind ourselves, though, what happened in this algorithm, and then we're going to prove that this algorithm does indeed reverse a string. So this is called reverse string, and remember what happens over here in the left box here, the blue box. We send in a string, and then it's supposed to output the reverse of the string. It starts out by saying if S is the empty string, then return S. So it's not going to do anything to the empty string because the reverse of the empty string is still the empty string, right? So it's not going to have to do anything. But then if that's not the case, then it goes and does these things. And if you remember, what we did was we would take off the first character of the string and then call reverse string again. That's what makes it a recursive algorithm. It calls itself. And then once eventually it gets down to this basis of being the empty string, then it gets to start returning things. And it would first return the empty string. But then once it starts returning things, we see down here below the call of where it says reverse string, it says that we add that character that we took off of the front, we add it to the end. Okay, so that's what this algorithm does. And if you look over here on the right, starting out at the top, if we start with the string POT, we would remove the first character to get OT, and then we would call reverse string on OT. Then what we would do in that call is to remove the first character in OT, which would be removing the O, and we're left with T. Then we call reverse string T. Then we would remove the first character, and that's where we would get the empty string. So then we would finally be calling the reverse string algorithm on the empty string. That's the first time we can then start returning something because of this line that says the first string. I mean that if S is the empty string, then just return the empty string. So that would be the case here where we would finally return what you see down here at the very bottom. It says empty string. We would return the empty string. And then in this algorithm, they were calling what gets returned, they were calling that S prime, right? If you look over here in the algorithm, S prime equals reverse string S. So whatever we get from a call to reverse string, we would call that whatever we would get from that call, we're going to call it S prime. So we just we return the empty string, so we'll call that S prime. But then down below these calls, it says that's when we start adding the character that was taken away, add it to the end. So down here, we're kind of working our way back up here. S prime is empty string, but then we would add the character that had gotten taken away from that last iteration, and that was the T. So we'll add it. We're adding it to the end, whereas before it was at the beginning. In this case, we can't really tell because it's the only character in there. But we're putting it at what we would consider the end, and so we have just that string now called S that just has the letter T in it. Okay, then we would, whatever that was, we're going to now, that gets returned, and so that would be returned, and that would be called S prime. And then we do to S prime what we did to it before, and that is add the character that got taken away, add it to the end. So for this iteration here, the character that got taken away was the O, so we'll add O to the end on the right hand side. Okay, and so then that's what gets returned, and we'll call that S prime. And that's this first iteration that we finally did way back at the very beginning, and we're now supposed to, whatever character was removed from the front, we'll put it on the back, and so we'll put the P at the end, and so we have TOP. And we have indeed, then, we can tell by this example, anyway, that we did take the string POT and reverse it to TOP. So the result would be, what would be returned, and the final result would be TOP. So that works, looks like it works correctly, but we haven't proven that it works correctly for everything. So that's what we need to think about next. How do we prove that this algorithm works for any string that is input, that it will truly reverse any string that is input? Let's now prove that this algorithm works. So we'll be creating a proof of correctness for this recursive algorithm called reverse string. Now, what would we be trying to prove? Remember, we're trying to prove that it does what it says it does. What does it say it does? Well, it says it reverses the string. So we could say that our theorem is for every input string S, reverse string returns the reverse of string S. Okay, so basically it's saying, yes, the return from this algorithm is going to be the reverse of what was input. Okay, so we're going to prove this, and we will prove it by induction, and we'll say it's done by induction on the length of the string. We're going to start out by showing that it's true for the very base case, which is a string of length, 0, which is the empty string. We'll show that it works for that. Then, in a minute, we'll also then say, well, let's assume it works for a string of size k, and let's prove then that if it works for a string of size k, that it will also work for a string of size k plus 1. So if we can get all of that done, then we will have completed our proof. So let's start with this base case of the string being the string of length 0, which has no characters. So the base case S is a string of length 0. Since S has no characters, the reverse of S is S, which is the string returned by the algorithm, right? So, I guess we could say, it is kind of a trivial case, but the reverse of nothing would be nothing. So we say that yes, this works for when S is just that very simple empty string. Now the inductive step. So remember, the inductive step involves two parts, an assumption and then something we need to prove. Okay, so the assumption is going to be, and we remember we call that the inductive hypothesis. We're going to assume that for any k value greater than or equal to 0, this algorithm returns the correct output for a string of that length, k. So for any string of length k, being anything 0 on up, we're going to assume that it's true. And if that's true, then we need to try to prove that it also will return the correct output for strings 1 character longer. Okay, so now again, what we're trying to prove is that this works for a string of length k plus 1. So let's start looking at S. Assume that S is a string of length k plus 1. And we would need to somehow prove that what comes out of this out of this algorithm would be indeed reversed. So here's what we can do here now that we know how long our string is. Let's number the characters in S. So let's say that the first character is C sub 1, next character is C sub 2, and so on. And if this is a string of length k plus 1, then it will go all the way to C sub k plus 1. Okay, so that's just what we're going to call the characters in our string S, and it does have a length of k plus 1. Now, the first character, when we go to work with this algorithm, and if we put in that that string of length k plus 1, the first thing we would be doing would be removing the first character. So let's go ahead and do that. We'll say that we'll remove the first character, which is C sub 1. So now we just have a new string that just starts at C sub 2 all the way up to C sub k plus 1. Okay, so that would be the first thing we do. Up here in the right in this box, it's reminding us what we do, and that's the first thing we would do. Let C be the first character and then remove it. Okay, now then the algorithm is going to make a recursive call with this new input of this new string that's missing the first character, and it starts at C2 up to CK plus 1. But now here's where we get to use our assumption. This string that's left, C sub 2 up to C sub k plus 1, it has k characters. And we're assuming that inductive hypothesis is assuming that this algorithm works for any string of k characters. So we would have to assume that this algorithm works for this new string that starts with C sub 2 and ends with C sub k plus 1, that it really does reverse that, right? So if it really does reverse that, then it would return the string C sub k plus 1, C sub k, all the way, and then the last character would be C sub 2. Okay, so we're assuming that it worked for any string of length k, so we're assuming it worked for this new string, and so we're going to just be reversing it, and we would say we know that this is what comes out of it, assuming that it does work for strings of length k, we would get this. This is what would come out of it. But then remember what ends up happening in this algorithm. After something is returned, then it says that S becomes what got returned, but we add that character that got taken away, we add it to the end. So after, when we got that return, the return of C sub k plus 1 all the way down to C sub 2, then the algorithm would add the C sub 1, that one character that originally got taken out. We're going to add that to the end of this string, to the right hand side of the string, which would then make this string look like this, where C sub k plus 1, C sub k, all the way down to C sub 2, C sub 1. And looking at that, we see that yes, that truly would be the reverse of what we started with. So by assuming that it worked for a string of length k, then we did what we needed to do for that string of length k. I mean, we started with a string of length k plus 1, but then by going through that first step, we turned that into a string of length k, and then could make the assumption it worked for that. And then we saw how once we then took that string of length k and added that new character in, we could examine those actual characters and see that that is really the reverse of what was put in. So that would be what we would need to prove. So we've proven, we've assumed it works for a string of length k, we've shown that it works for a string of length k plus 1. Since we did that and we also showed it for the base case, then by induction we can say that we have proved that this algorithm does what it says it's supposed to do. Here's another algorithm that we talked about last time. It was called the recursive algorithm to compute the power set of a set. Remember, we start with a set we'll call A, and then the power set of that we could denote as capital P of A. That would be, if it's the power set, that means it's the set of all subsets of A. So let's look at this algorithm, remind ourselves what was done, and then we'll go into creating a proof of correctness for this algorithm. So we started, again, this algorithm, it starts with its name, so it's called power set, and then we see that we send in a set for the input, and what we get out of it is the power set. And then we have this base case that if the set A is just the empty set, then we don't return the empty set, because remember, this power set is going to be a set of sets. Okay, the elements in the power set are actually sets themselves. So we would return the set that includes the empty set. Okay, now we then did some things. Remember, we would take out an element and then call the power set algorithm again, and then do some things here on the tail end. So let's kind of take a look here and say, look at this example here again, that where we're taking the set ABC. And so the first time through, we would skip this one that says if A is the empty set, because it's not. We would go on and we'd say, okay, we need to remove an element from our set. So this first time we removed the A. And then it would call itself again on that. So then we're told again to remove another element. So we'll remove B for the second time. The third time we'll remove the C. And by that time, we've ended up with the empty set. So we would be calling power set on the empty set. So then we see that it says, you know, if A is the empty set, return the set of empty sets. So that's why we see this down here at the bottom right, return the set that holds only the empty set. Now, what we do on the tail end of this is that we're going to, whatever gets returned, we're going to call that P prime. And then what was also returned, we're going to then add some extra things in there. So what it told us to do was that we're supposed to, whatever got returned in the previous iteration, we'll call that P prime. And then we'll let P be everything in P prime, along with any along with what started out in P prime with the character, or with the element that was taken out in that iteration added back in. So this last iteration, C had been taken out, so we'll put C into the empty set, and that gives us a set just that includes only C. So we take a copy of the P prime and then also, though, put in those extra new sets that will be anything that was in P prime with also that one element added back in. So this first time we just get this new P here. Then for the next iteration, P prime is going to be what we ended up with for P the time before. So here we would have the empty set and then the set including only the element C. But now we take a copy of that, and so we want all of that along with the sets that we would get when we add back in that one element we had just taken away for that iteration, which was a B in this case. So along with the empty set and the set that just involves C, we'll put in a B to each of those two sets. So when we put a B into the empty set, we just get the set B. When we put a B into the set C, we get CB. And so now we have all four of those sets. And then that's what gets returned for the initial iteration. And so we'll call that P prime. And then again, see what got taken away in that iteration, and that was an A. So P prime's P, the new P, is going to have everything that's in P prime, but then we'll also put the A into each of these that are in P prime, and so we'll get four new sets too. So we get to start with these first four sets that were in P prime, but then when we put an A into the empty set, we get the set just with A. When we put an A into the set called with just a C in there, we'll get CA. When we put A into this set that just has B in it, we get BA, and then when we put A into the set CB, we would get CBA. And remember, with sets, it doesn't matter the order that we list our elements. It's the same set. If I put it in an order, you put it in a different order, it still represents the same set. So anyway, that then is what we get for P, and then we're told to finally, once all of this gets done and we get back to the initial iteration, then we return what was in our capital P, and so we would be returning this, and this would be our power set. Okay, so this was the recursive algorithm. Now we just need to come up with a proof of correctness for it. So I have the algorithm again over here in the box on the right, and we're going to just kind of go over the general idea of what we need to do here first before we actually dive into doing it. This one does involve a little bit more than what our last proof did. The last proof, it was pretty simple. We got to our, we were able to prove what we needed to prove, pretty quickly. This one, we've got some different cases, different situations, so we have to prove some different things. So this one's a little bit more involved. So first of all, let's start by just kind of going over our kind of our game plan for this. So the theorem, we need to prove that for any finite set A, and anyone, right? That's we've seen that example for that one, but that doesn't prove that it works for everything. So for any finite set A, power set of A is going to return the correct power set of A, right? Just because we call it power set doesn't mean it really returns the power set. So we need to see if we can prove that this correctly does return the power set. And we're going to again use proof by induction, and here on the size of the input set A. Okay, so that's what we're going to do here. We're going to first of all, for the base case, show it's true when the size is as small as possible, and that would be that base case of where A is just the empty set. Right? If the size of A is 0, that's the smallest we could get, then that would mean that A is the empty set. And so if the empty set is input into this algorithm, then we see that what would be returned would be the set that includes only the empty set, because of this first statement that says if A is equal to the empty set, return the set including only the empty set. So, and that we can think about it, does that set that includes the empty set, does that include all of the subsets of A? Yeah, remember a set is always a subset of itself, so the empty set would be a subset of the empty set. So that's the one set that is in our power set for this empty set as the input, and that is just the set that includes only the empty set. Okay, so we've just proven the base case right there, that it's it's easy to find what the power set of that set would be, and yes, it's true that the algorithm does return that correct one. But then we would need to go to the inductive step, and if we're going to use induction on the size of input set A, then we would want to say something like, let's assume it works for a set of size k, and then show it also works for a set of size k plus 1. So that's what we're going to do. So the inductive hypothesis, the assumption, is that the power set algorithm works correctly on an input set of size k, and then we want to show that it also, if we can make that one assumption, we'll also then try to prove that it also works for a set of size k plus 1. Now let's get some terminology down before we get going on this proof. Let's say that A is our set with k plus 1 elements, because remember, that's kind of what we're trying to prove, that this works for size k plus 1. So let's say that A is a set with k plus 1 elements. Then what would happen is the algorithm would remove an element from the set and then would get a new set, right? Because that's the first thing that's done over here in the algorithm. We remove an element. So when we remove that first element, let's say that we remove, and they call this element that gets removed in the algorithm, they call it little a. Okay, so we're going to have a picture here where we have big A, which is the entire set that has k plus 1 elements. We see this little element here called little a, and that's the one we're going to take out. So then if we take that out, we'll call everything else, the set with that A taken out, we're going to call it A prime. Okay, so A is the original set. A prime is what we get when we take out one of the elements. Okay, and how big is A prime? Well, A started out with k plus 1 elements. We took out one element, so the size of A prime is going to be size k, right? Because we took out one element. So, anyway, let's say that P prime is the set returned by calling the algorithm on A prime. And that's what ends up happening in this algorithm here. So once something gets removed, then we get something returned, and that ends up being the power set of what we just worked with. Okay, so P prime is not necessarily the power set, because we haven't proven that yet, but we're going to say that P prime is whatever gets returned when we put in A prime, okay? And then P is what gets returned when we send in the entire set of A, okay? So it's just we're calling what gets returned, calling it P prime if we've just returned in a new set that is missing an element. But P is what we're calling it when we get a return from the entire set A. Now, what would the inductive hypothesis say? Well, it says that P prime, remember, that's what gets sent back, returned on the set A prime once we've taken an element away. So the inductive hypothesis says that P prime is exactly the power set of A prime, right? We're saying, yes, we're going to assume that this algorithm really does return the power set, because that's our because it's of size k. So, and that's our assumption that the power set works correctly on an input set of size k. Okay, so that would be the inductive hypothesis. Then what we'll do is use that inductive hypothesis to show that P, which is this what gets returned when we put in this larger set that has one more element, show that P actually is the power set of A. So that it worked. That's what we're trying to prove, that it worked on this new set of K plus 1 elements. So we're assuming that P prime is in fact the power set, and we want to show that we're assuming that P prime is in fact the power set of A prime. And so now we want to show that P is in fact the power set of A. Okay, so that's our goal. That's what we're going to try to prove. So we'll get started. As I said, it's not as simple as that last proof that we did. So we're on the inductive step. We're going to assume for the inductive hypothesis that P prime, what comes out of the algorithm if we pass in A prime, is truly the power set of A prime. Remember, A prime is of size k, and A has one element more than A prime. So A is of size k plus 1. So we're assuming this algorithm works for a set of size k, and then trying to show that it's also true for a set of size k plus 1. Okay, now remember that P prime is what's returned from the algorithm. That we are assuming is truly the power set. Then P is what's returned by the algorithm when we pass in A. We haven't shown yet that that's truly the power set. We know it's what's returned, but we don't know that it's the power set yet. That's what we're trying to prove. Now, here's what we have to do in order to prove that. We're going to first prove that if we've got some subset of A, we'll just call that X. If X is some subset of A, then X will end up being in P, which is what's returned. Okay, so that means all the subsets of A are going to be in there. Later, we'll need to show that everything that's in P does end up being a subset, right? Because we can't have maybe the power set along with some other things in there too. We have to show that everything in the power set or everything in P is actually a subset of A. So that second part we'll need to prove later. But this first part here we're going to prove now, that if we have some set that we know is already know is a subset of A, then it's going to show up in P, and P is what's returned by that algorithm. Okay, so now the thing is we've got two cases here we need to consider. We might be talking about a set that doesn't include that first element that we take out as in that algorithm. Remember, the first thing that we do when we go when we would be going from A down to A prime is we'd be taking out an element. And so maybe this general set that we're saying is a subset of A, maybe it doesn't involve this little element A that we have taken out as one of the first things we do. But maybe it does. So in that case, it would look like what's on the right. This X would be some stuff in A prime, but then also include that A. So those are the two different cases we're going to need to prove this for. So let's start with case 1, where we say, okay, these sets that are subsets of A, are they all going to end up in P? So here's we're assuming that this subset of A does not include this little element that is taken out first. Okay, so A, that little element that's taken out during that iteration, is not in this X that we're talking about, which is just a general subset of A. So all of these subsets that don't include A, are they all going to end up in P? Okay, well, let's think about this. If A is not in X, then X is totally enclosed within A prime, right? There's no part of X that's outside of A prime. So X is a subset of A prime. And remember, we're assuming that this algorithm works for a set of size k, and A prime is size k, and so we're going to assume that this algorithm gives us truly the power set of A prime. So if that's the case, then P prime is the power set, the real power set of A prime, and so so it is. So since X is a subset of A prime, then it would show up in that true power set of A prime, which is P prime. Okay, so in the algorithm, the P that we end up with after we, put in the capital A, that's what P is. It's obtained by taking what was in P prime and then adding more to it. Okay, so I guess let's just say it that way for this step here, that if X is already in if X is a subset of A prime, then it's going to be in P prime, and it's going to be in the power set of A prime. But therefore, it would also be in the power set for A. It's going to be in P because we get P by just adding things in. So if it's in P prime, it's also going to be in P. So X is also going to be in P. So we've shown that in this case, any set that's a subset of A prime that doesn't include that first little element that's taken out, it is going to end up being in P. And again, let me see if I can restate that in the clearest possible way. In this case here, we see that X is a subset of A prime, and we can assume then that X will show up in P prime because we're assuming it works, this algorithm works correctly for that size. So X is going to show up in P prime, but will X show up in P? That's the question. But it will, because remember we said to get from P prime to P, we take everything in P prime and then add more into it. So if X is going to show up in P prime, it will also show up in P. But now let's look over in this case number 2, where what about the sets that are subsets of A, but they include that one little element that's taken out? We have to again show that sets like this will also, if it starts out here as in this picture where it's a subset of A, even though it includes that little element that gets taken out, we have to show that it also is going to show up and come out of what the algorithm returns, which is the P. We have to show that X is going to be in that P. So we're assuming that A is part of X. A is an element of X. Okay, so if A is an X, then let's take A out of it. So we have the set X minus A. Well, that little bit right there, the X minus A, that's a subset of A prime, right? X minus A is a subset of A prime. You can see there. Now we're assuming that this algorithm works correctly on an input set of size k. So therefore, I would know that X minus A, which is a subset of A prime, it should show up in P prime, because we assume that this algorithm works correctly, right? So we assume that P prime is the true power set. So we would know that X minus A is going to show up in P prime. But how will that let us know that x is going to show up in P? Well, if x minus a shows up in P prime, then when we add that one little element that got taken out to begin with, add it back into the x minus a, we're going to have this, what's in blue and red. X minus a, that's when we got taken out of a, then we add a back in. That's what's going to happen when we construct P because of this part here in the box. This is a part of the algorithm that says we start with the P prime and then we take everything in P prime and then also add a back into it, and that gets put into P. So adding a back into x minus a is going to then, we see, become part of P. So for case 2, we've shown that even if this set includes the a, the thing that gets taken away, and we're assuming it's a subset of a, that will show up in what's returned for P. So anything that's a subset of A is going to show up in what's returned for P. But now we need to show the other way. So we've already shown that if we've got a subset of A, if X is a subset of A, then X shows up in P. Now we need to show the other side to it, which is if X is in P, if it's a set in P, then it truly it's a subset of A, okay? That there's not extra stuff in P, that it's truly the power set only has those subsets of A. So we need to show that. Okay, so any set that's added to P, remember when we go from P prime up to P, any set that's in P is either already going to be in P, or it's going to be something where it was started out in P prime and then we added that extra element back in, right? So like take any of these P primes to get to the P above it. We take everything in P prime and then add what was in each of those sets, add in that one thing that was taken away. And in the case that we'd be talking about, we'd be adding back in the A. Okay, so if it's in P, and we're assuming it is in P, then it's either a subset of A prime, or we're going to then just be adding in A into it. So therefore, if a set is in P, then that set's going to be a subset of A, because in this first case, this first bullet point, if it was already in P prime, it was a subset of A prime, and therefore it would be a subset of A. But if it's the second bullet, then we know that, S is a subset of A prime, and then all we did was add in one little element that we know is in A. So we know that also would be a subset of A. Now, I don't know if this is making any sense to you at all. I know it gets a little bit complicated, but anyway, we've proven this other way here now. So this would then complete the proof. Remember, overall, what did we show? We showed that what gets returned by the algorithm is true for that base case, that very small case of when A is the empty set. Then we said, let's show that what's returned, let's assume what's returned by the algorithm is truly the power set for any set that's of size k. And then we said, well, now let's look at this set of size k plus 1. We're going to call that A, that set A. And we showed that if we have a set that's a subset, it does show up in P. And then we also showed that if we have something in P, it really truly is a subset of A. So because of all of that, then now we can say that we have proven this theorem, the proof of correctness for this. Now, as I said, this has been kind of complicated, and you might have gotten lost a little bit along the way. So don't so much worry about that. You won't have to come up with an entire proof or anything, but you really do need to, again, be aware of the different parts of this proof. We proved the base case. Then we made the assumption it was true for a set of size k, and then we used that to prove that it was also true for a set of size k plus 1. It's that overall overview that I want you to really be to understand and be familiar with.